Picture this: a place where gravity is so intense, not even light can escape its grasp. A void so powerful it twists time and space into knots. Black holes are just one example of the universe's most extreme environments, realms where the laws of physics are pushed to their absolute limits. But they're not alone. From the searing fury of supernova to the icy, desolate plains of rogue planets adrift between galaxies, the cosmos is filled with places that defy imagination. These aren't just distant curiosities, they're the ultimate tests of what's possible, where matter, energy, and even reality itself behave in ways that seem ripped from science fiction. What if I told you there's a star so dense, a single teaspoon of its material would weigh as much as a mountain, or a storm on a distant planet where winds scream at speeds faster than a bullet? These aren't fantasies, they're real, documented wonders, each more bewildering than the last. The universe doesn't just dabble in extremes, it writes the rulebook on them. And every discovery we make peels back another layer, revealing just how little we truly understand about the fabric of existence. This isn't just about cosmic spectacle, it's about uncovering the very boundaries of what's possible, and in doing so, redefining our place in the grand scheme of things. That's exactly what we're diving into today. Over the next 30 facts, we'll journey to the most hostile, bizarre, and awe-inspiring corners of the cosmos. Places where temperatures soar to millions of degrees in an instant, where magnetic fields could shred atoms, and where time itself slows to a crawl. Some of these environments are so alien, they challenge everything we thought we knew about survival, physics, and even the nature of reality. So buckle up, because by the end of this, you won't just see the universe differently. You'll feel it, the scale, the violence, the beauty, it's all out there waiting to be explored. Let's begin. The Phoenix Cluster holds a record that sounds like something out of myth. Its central galaxy is the hottest place ever discovered in the observable universe. Here, temperatures soar to an almost incomprehensible 500 million degrees. That's hotter than the core of our sun multiplied by 30. What could possibly generate such blistering heat? The answer lies in the heart of this galaxy, where a supermassive black hole isn't just lurking, it's feasting. As matter spirals toward the black hole's event horizon, friction and immense gravitational forces rip particles apart, heating them to temperatures that rival the Big Bang itself. But here's the real puzzle. Galaxy clusters like this one should cool down over time. Hot gas typically radiates energy away, condensing into new stars. Yet the Phoenix Cluster defies that logic. The black hole's violent outbursts pump so much energy back into the surrounding gas that it can't cool effectively. It's like a cosmic oven stuck on broil. This creates a turbulent feedback loop where heat begets more heat, and the cycle continues. Astronomers call it violent quiescence, a paradoxical state where chaos and stability collide. This extreme environment isn't just a spectacle, it's a window into how galaxies evolve. The Phoenix Cluster challenges our assumptions about how black holes shape their surroundings. Instead of merely devouring matter, they can also regulate an entire galaxy's growth, like a furious conductor directing an orchestra of gas and stars. Without these seething crucibles, the universe as we know it might look entirely different. So the next time you feel a summer heat wave, remember, out there in the depths of space, there's a place where hot doesn't even begin to describe it. If you think space is cold by default, the Boomerang Nebula will redefine your understanding of frigid. This cosmic oddball holds the title of the coldest known natural place in the universe, with temperatures plummeting to a jaw-dropping 1 Kelvin. That's negative 458 degrees Fahrenheit. To put that in perspective, even the vast emptiness between galaxies isn't this cold. The cosmic microwave background, the afterglow of the Big Bang, lingers at a balmy 2.7 Kelvin. So how does the Boomerang Nebula manage to undercut even that? The secret lies in its explosive farewell. This nebula is the aftermath of a dying star, but not just any death, it's a hyper-chilled finale. As the star shed its outer layers, it didn't just eject material gently, it blasted it outward at speeds nearing 164 kilometers per second. That's like emptying a bathtub by flinging the water out with the force of a rocket. This rapid expansion caused the gas to cool dramatically, a phenomenon similar to how aerosol cans feel cold when sprayed. The faster the gas expands, the more heat it loses, and the Boomerang Nebula essentially turned itself into the universe's most efficient refrigerator. But here's the twist: this nebula isn't just cold, it's unnaturally cold. Even in the depths of space, where temperatures routinely hover near absolute zero, the Boomerang Nebula stands out. Its unique structure plays a role too. Unlike most nebulae, which are roughly spherical, this one has twin lobes of gas that give it a bow tie shape, hence its name. Those lobes act like cosmic air conditioners, allowing radiation to escape more efficiently and dragging temperatures down even further. What's truly mind-bending is that this nebula defies expectations. When astronomers first measured its temperature, they double-checked their instruments, convinced there must be a mistake. But no, this relic of a star's death is a laboratory of extreme physics, showing us how the universe can wring out every last drop of heat from a system. It's a reminder that even in the vast, silent stretches of space, there are places where the rules get twisted into something extraordinary. So the next time you shiver on a winter night, remember, somewhere out there, there's a patch of the cosmos where winter never ends, and cold isn't just a condition, it's an art form. Imagine an explosion so powerful it can outshine 1,000,000 trillion suns for just a few seconds. Gamma-ray bursts are the universe's ultimate fireworks, cosmic detonations so intense they release more energy in a blink than our sun will over its entire 10-billion-year lifetime. These aren't just bright flashes, they're the universe's most violent and radioactive environments, capable of sterilizing entire galaxies in their path. And the scariest part, we still don't fully understand what triggers them. The leading theory points to the collapse of massive stars dozens of times heavier than our sun. When these giants die, they don't just fade, they implode with such force that their cores collapse into black holes or neutron stars, while their outer layers are ejected at nearly the speed of light. This produces twin jets of gamma radiation, the highest energy form of light, which punch through space like cosmic blowtorches. If one of those jets happened to be aimed at Earth, even from thousands of light years away, it would ionize our atmosphere, strip away the ozone layer, and potentially trigger mass extinctions. But gamma-ray bursts aren't just destructive, they're also mysterious. Some last only milliseconds, hinting at collisions between neutron stars. Others linger for minutes, suggesting the death throes of hypergiant stars. And then there are the outliers, bursts so energetic they defy current models, like one recorded in 2020, nicknamed the Boat, the brightest of all time. Detected over 2 billion light-years away, it flooded telescopes with enough radiation to temporarily blind some instruments. What makes these events truly extreme isn't just their power, it's their aftermath. The radiation lingers, creating shockwaves that can travel through interstellar gas for millennia. Any planet caught in the crossfire would be bathed in lethal doses of X-rays and gamma rays for years, turning even a habitable world into a radioactive wasteland. Yet paradoxically, these bursts might also seed the cosmos with heavy elements like gold and platinum, forged in the furnace of the explosion. So while gamma-ray bursts are terrifying, they're also cosmic alchemists, destroyers, and creators wrapped into one. They remind us that the universe doesn't just operate in extremes, it thrives on them, rewriting the rules of physics in bursts of light that echo across the cosmos. And somewhere out there, right now, another star could be winding up for its final, catastrophic performance, a reminder that even the quietest corners of space hold the potential for unimaginable fury. Neutron stars are the universe's ultimate Densalab experiments, packing the mass of a sun into a city-sized sphere. But it's not just their density that's staggering, it's their gravitational grip. Near the surface, gravity is 100 billion times stronger than Earth's, a force so overwhelming it bends light into a curve and distorts the very fabric of spacetime. If you were to hover just a few kilometers above one, not that you could survive the attempt, the difference in gravity between your head and your toes would stretch you like taffy in a process called spaghettification. Atoms, normally resilient little structures, would be ripped into elongated strands, their electrons torn from their nuclei in a cosmic tug of war. This isn't just theoretical. In 2017, astronomers witnessed a neutron star's gravitational might firsthand when two of them collided. The event sent ripples through space-time gravitational waves that detectors on Earth picked up. But what happened next was even more revealing. The merger forged heavy elements like gold and platinum in seconds, proving neutron stars aren't just destroyers, they're cosmic forges, crushing matter so violently that new elements are born in the chaos. What makes these stellar remnants truly extreme isn't just their gravity, it's how they weaponize it. Some neutron stars, called magnetars, couple that gravity with magnetic fields a quadrillion times stronger than Earth. If a magnetar lurked halfway between us and the moon, its magnetic field would erase the data on every credit card on the planet. But even ordinary neutron stars warp reality in ways that seem ripped from science fiction. Time itself slows near their surfaces. A clock ticking there would fall behind one on Earth by about 34 minutes every year. Yet for all their fury, neutron stars are precise cosmic clocks. Many spin hundreds of times per second, flashing beams of radiation like lighthouses with metronomic regularity. These pulsars helped confirm Einstein's theory of general relativity, their rhythmic pulses serving as nature's most accurate timekeepers. So while neutron stars are laboratories of extreme physics, they're also the universe's way of showing us just how far the rules can bend before they break. And somewhere out there, right now, one of these ultra-dense remnants is warping space, twisting time, and reminding us that gravity isn't just a force, it's a sculptor, shaping the cosmos in ways we're only beginning to understand. Winds on Earth can topple trees and strip roofs from houses, but out in the cosmos, there are gales so fierce they could shred entire solar systems. Around black holes and pulsars, winds don't just blow. They scream across space at millions of miles per hour, reaching speeds that make hurricanes look like gentle breezes. Take the black hole system IGRJ 17091 for example. Here, winds whip around at nearly 20 million miles per hour. That's about 3% the speed of light. At that velocity, these aren't just streams of particles, they're cosmic sandblasters, carving through clouds of gas and dust with enough force to alter the fate of entire galaxies. What fuels these supersonic tempests? It all comes down to sheer gravitational violence. As matter spirals toward a black hole or gets flung outward by a pulsar's magnetic field, it doesn't just drift, it accelerates to unimaginable speeds, heated to millions of degrees by friction and radiation. The result is a plasma wind, a supercharged gust of charged particles that carries enough energy to push star-forming gas clear out of a galaxy's reach. In some cases, these winds are so powerful they create vast empty bubbles in space, regions where no new stars can form. But here's the twist, these destructive gales might also be cosmic architects. In the Crab Nebula, the pulsar at its heart spins 30 times per second, its magnetic field flinging particles outward in a relentless gale. That wind collides with slower-moving debris from the supernova that birthed it, sculpting intricate filaments and shockwaves that glow across the electromagnetic spectrum. Without these extreme winds, the nebula would look entirely different, a reminder that even the most violent forces can shape beauty. And then there's the black hole at the center of galaxy PDS 456, where winds don't just blow, they roar in multiple directions at once. Observations show these gusts aren't uniform. They're chaotic, like a storm with no eye, capable of ejecting enough material to starve the black hole itself of fuel. It's a self-regulating system where the very winds that could stifle star formation also prevent the black hole from growing too greedy. So while these cosmic hurricanes might seem like pure destruction, they're also part of a delicate balance. They clear the way for new stellar generations, they carve structures into the void, and they remind us that even in the most extreme environments, chaos and creation are two sides of the same coin. Next time you feel the wind on your face, remember, out there, it's moving fast enough to rewrite the universe. Neutron stars aren't just dense, they defy the very laws of ordinary matter. Picture scooping up a teaspoon of material from one of these cosmic remnants. That tiny spoonful would weigh around 1 billion tons, more than the combined mass of every car on Earth. It's as if you compressed Mount Everest into a sugar cube. This staggering density occurs because the star's core collapse crushes atoms beyond recognition. Electrons, normally orbiting at a safe distance, get slammed into protons, transforming them into neutrons. The result, a seething ocean of subatomic particles packed shoulder to shoulder, with no empty space left between them, a state physicists call neutron degenerate matter. But here's where it gets stranger. At these extremes, the rules of quantum physics take over. Neutrons, which usually stick to their own kind, get forced so close together that they start overlapping, creating a bizarre quantum soup. Under normal conditions, this would be impossible, like trying to stack marbles without them rolling away. Yet inside a neutron star, gravity's relentless squeeze overrides every repulsive force, pushing matter into territories we can't replicate in any lab. Some theories even suggest the cores of these stars might harbor yet stranger substances, quark-gluon plasma, where neutrons break apart into their fundamental components, or hyperons, exotic particles that flicker in and out of existence under the crushing pressure. What's truly mind-bending is how neutron stars expose the limits of our knowledge. Take their crust, for example. It's not solid in any familiar sense. Instead, it's a lattice of atomic nuclei swimming in a sea of free electrons, a metallic layer so tough it could support mountains taller than the Himalayas, despite being just a kilometer thick. And if that weren't surreal enough, the surface might be dotted with nuclear pasta, a phase of matter shaped by competing forces into structures resembling spaghetti or lasagna sheets. These aren't metaphors, they're real classifications physicists use to describe matter under conditions so extreme, it behaves like nothing on Earth. Then there's the star's interior, where pressures mount so high that neutrons themselves might align into streams or vortices, creating a superfluid, a frictionless state where matter flows without resistance. Add rapid rotation to the mix, and you've got a celestial blender, spinning hundreds of times per second while its core dances to the tune of quantum mechanics. Neutron stars are cosmic paradoxes, both perfectly smooth and unimaginably rugged, unimaginably dense yet governed by the fuzzy laws of quantum uncertainty. They're reminders that the universe doesn't just push boundaries, it shatters them, leaving us to piece together the fragments with equations and wonder. And every new observation, every gravitational wave detection, peels back another layer of their mystery, proving that even in the most forbidding corners of space, nature still has tricks up its sleeve. The Hercules Corona Borealis Great Wall isn't just large, it's a cosmic titan so vast it shouldn't exist. Stretching an astonishing 10 billion light-years across, this filament of galaxies and dark matter forms the single largest known structure in the observable universe. To grasp its scale, imagine a thread so long it could wrap around the Milky Way more than 30,000 times. This isn't merely a cluster or supercluster. It's a colossal web of matter, a skeleton of the cosmos so immense it challenges our fundamental understanding of how the universe organizes itself. What makes this structure truly baffling isn't just its size, but the fact that it defies one of cosmology's bedrock principles, the cosmological principle. This idea states that on large enough scales, the universe should appear roughly uniform, with matter distributed evenly in all directions. Yet the Great Wall contradicts that, presenting a glaring anomaly. Its existence suggests there might be limits to how far this principle holds, or that we're missing something profound about the universe's architecture. The discovery itself was a stroke of cosmic detective work. Astronomers mapping gamma-ray bursts, those universe-shattering explosions we discussed earlier, noticed an eerie pattern. These bursts weren't scattered randomly, they traced a faint, gargantuan arc across the sky. Each burst acted like a flare, marking the position of distant galaxies. When researchers connected the dots, the outline of the Great Wall emerged, a curtain of matter woven into the fabric of space-time. But here's the real mystery: how could something this colossal form in the first place? The universe is only 13.8 billion years old, and the Great Wall spans nearly 3/4 of that distance. Even accounting for expansion, it shouldn't have had enough time to coalesce under gravity's pull. Some theorists speculate it might be a relic of primordial density fluctuations, seeds planted in the universe's infancy that grew unchecked. Others wonder if it's not one structure at all, but a chance alignment of multiple filaments, a cosmic illusion on a grand scale. Yet the implications go deeper. If structures like this are possible, our models of cosmic evolution might need revisiting. Dark energy, the mysterious force accelerating the universe's expansion, should be tearing such vast assemblies apart. The Great Wall's persistence hints that gravity and dark energy engage in a tug-of-war we don't fully understand. And then there's the haunting question: is this truly the largest structure, or just the largest we've found so far? Our telescopes can only peer so far into the cosmic deep. Beyond that boundary, who knows what other titans might lurk, waiting to redefine our sense of scale once again. The Hercules Corona Borealis Great Wall isn't just a curiosity, it's a challenge, a cosmic dare to rethink everything we thought we knew about the universe's grand design. Among the universe's most destructive forces, magnetars stand in a league of their own. These aren't just neutron stars, they're cosmic monsters armed with magnetic fields so intense they defy reason. We're talking about fields a quadrillion times stronger than Earth's. Forces so powerful they could strip the electrons from your atoms before you even realized what was happening. At a distance of 1,000 kilometers, a magnetar's magnetic grip would liquefy every molecule in your body, warping the very bonds that hold matter together. But how does something this extreme even form? Picture a neutron star, already a collapsed core of a dead star, spinning at breakneck speeds with a dynamo of superheated, electrically charged plasma swirling in its interior. When conditions align just right, that dynamo amplifies the star's magnetic field to ludicrous levels, transforming it into a magnetar. The process isn't gentle. It's like revving a jet engine until it explodes, except here, the engine is a city-sized object with the mass of a sun. The consequences of such ferocious magnetism are nothing short of apocalyptic. Magnetars don't just sit quietly in space, they erupt. Starquakes, the neutron star equivalent of earthquakes, fracture their surfaces when the crust, strained by twisting magnetic fields, suddenly snaps. These aren't tiny tremors. A single starquake can release more energy in 1/10 of a second than our sun emits in 100,000 years. In 2004, a magnetar 50,000 light-years away let out a scream so loud it briefly ionized Earth's upper atmosphere despite being halfway across the galaxy. And then there's the magnetic field's most bizarre trick. It can literally bend reality. In a magnetar's presence, empty space itself becomes distorted. Quantum fluctuations, the ghostly particles that pop in and out of existence, get stretched and squeezed by the field's influence, creating conditions where matter behaves in ways no lab on Earth could replicate. Even light doesn't escape unscathed. Photons passing near the star twist and split, a phenomenon called vacuum birefringence, as if space itself has become a funhouse mirror. Yet for all their fury, magnetars are also cosmic lighthouses. Their magnetic fields channel radiation into narrow beams that sweep across the universe, detectable as bursts of X-rays or gamma rays. Some flicker like strobe lights, others erupt in unpredictable tantrums. Each outburst is a message, a clue to understanding how matter behaves under conditions so extreme they border on the surreal. So while magnetars might seem like agents of pure destruction, they're also nature's most ruthless physics instructors. They show us the limits of magnetic fields, the breaking points of matter, and the sheer audacity of a universe that doesn't just push boundaries, it vaporizes them. And somewhere out there, right now, one of these magnetic leviathans is winding up for its next cataclysmic lesson. HD 189,733b isn't just another exoplanet, it's a nightmare world where the weather would make even the fiercest earthly storms seem tranquil. Imagine standing on its surface if you could survive long enough to try. The first thing you'd notice, blistering winds roaring at 5,400 miles per hour, fast enough to outpace a speeding bullet 7 times over. These aren't gentle breezes, they're supersonic cyclones tearing across the planet with enough force to strip flesh from bone. But the winds are just the opening act. Look up and you'd see a hellish rain not of water but of molten glass. That's right, droplets of superheated silica propelled sideways by those monstrous gales, creating a horizontal hailstorm that would flay anything in its path. What makes this cobalt blue world so vicious? Its proximity to its host star plays a starring role. Orbiting a mere 3 million miles away, 13 times closer than Mercury hugs our Sun, HD 189,733b is tidally locked, with one side perpetually scorched and the other trapped in eternal darkness. This extreme temperature contrast fuels those relentless winds, as gases rush from the dayside's inferno to the nightside's frozen wastes, only to be superheated and hurled back again in a never-ending loop of atmospheric fury. But here's where it gets even stranger. The planet's vivid blue hue might trick you into thinking of Earth's oceans, until you learn the color comes not from water, but from a haze of silicate particles in its atmosphere. These microscopic shards scatter blue light while absorbing red, giving the sky a deceptively serene appearance. It's a cruel illusion. Those same particles, heated to thousands of degrees, are what condense into the glass raindrops that perpetually pelt the planet's surface. Yet for all its hostility, HD 189,733b is a goldmine for astronomers. Studying its atmosphere has revealed how exotic chemicals like sodium, methane, and carbon dioxide behave under extreme conditions, clues that help us decode the diversity of exoplanets. When scientists observed water vapor in its skies, they expected a familiar sight. Instead, they found water molecules being ripped apart by the planet's vicious winds, a process that could never occur on Earth. This world also raises a tantalizing question. How many other hot Jupiters out there hide similar extremes? HD 189,733b is far from alone in its brutality. Its lessons warn us that not all blue planets are havens, and that the universe has a flair for crafting horrors as creatively as it crafts wonders. So while we may never set foot there, this glass-raining monster serves as a vital reminder: the cosmos doesn't cater to our comforts. It's a laboratory of the extreme where the rules defy expectation, and every discovery peels back another layer of the impossible. TRS-2b isn't just a dark planet, it's the darkest world ever discovered, a place where light goes to die. This gas giant, orbiting a star 750 light-years away, reflects less than 1% of the sunlight that hits it. To put that in perspective, even coal, one of the darkest substances on Earth, reflects about 4%. Standing on this planet, if you would feel like being trapped in an endless void, darker than the blackest ink, with only the faintest glow from its searing hot atmosphere to hint at its presence. So what makes TRS-2b such a cosmic vampire? The answer lies in its eerie atmosphere. Unlike Jupiter, which bounces back a third of the light it receives thanks to bright ammonia clouds, this planet's skies are stripped of reflective particles. Instead, they're choked with vaporized sodium and potassium, gases that absorb nearly all visible light. But the real kicker, its atmosphere might also contain exotic compounds like titanium oxide or gaseous vanadium materials so efficient at swallowing light that they turn the planet into a near-perfect blackbody. Here's the twist though, TRS-2b isn't cold. Its day side simmers at around 1,800 degrees Fahrenheit, hot enough to glow a dim, hellish red. Yet even that thermal radiation is barely detectable. The planet's atmosphere is so adept at absorbing light that it traps almost all energy, irradiating it as heat in wavelengths invisible to the human eye. It's like a cosmic stealth machine hiding in plain sight by converting starlight into an imperceptible whisper. This bizarre world defies expectations. Planetary formation models suggest gas giants should have brighter, more reflective atmospheres, especially when they're this close to their star. TRS-2b's extreme darkness hints that we're missing something fundamental about how planets evolve under intense heat and radiation. Some scientists speculate its atmosphere might be locked in a perpetual chemical storm, with compounds constantly breaking down and reforming in ways that prevent any reflective layers from stabilizing. The discovery of TRS-2b forces us to rethink the very definition of a planet. We've long categorized worlds by their size and composition, but what about their light signature? If a planet can be this dark, what other extremes might exist? Worlds that absorb 99.9% of light, or ones that reflect none at all? TRS-2b isn't just an oddity, it's a challenge, proving once again that the universe has more imagination than we do. And as we keep searching, who knows what other shadowy surprises might be lurking in the cosmic dark. Imagine a world where volcanoes don't just erupt, they never stop. Jupiter's moon Io is the solar system's most volcanically active body, a place where the ground itself is in constant revolt. Over 400 active volcanoes dot its sulfur-stained surface, spewing lava fountains dozens of miles high and painting the landscape in vivid yellows, oranges, and reds. This isn't the occasional geological tantrum, it's a full-blown, non-stop fireworks display, reshaping Io's surface so rapidly that spacecraft images taken just months apart reveal entirely new flows and fresh scars from recent eruptions. What fuels this relentless fury? The answer lies in Io's tortured relationship with Jupiter. Locked in a gravitational tug of war with both Jupiter and its neighboring moons Europa and Ganymede, Io gets stretched and squeezed like a cosmic stress ball. These tidal forces generate immense friction within its core, heating the moon's interior to the point where rock melts on a planetary scale. Think of it as repeatedly bending a paperclip until it snaps, except in Io's case, the bending never stops and the snap is replaced by a continuous planet-wide meltdown. The result is a world where magma doesn't need to pool beneath the surface. It's everywhere, erupting through countless vents and fissures in rivers of molten rock. But here's the twist. Io's volcanoes aren't just violent, they're bizarrely efficient. Some eruptions are so powerful they shoot plumes of sulfur and silicate particles 300 miles into space, high enough to briefly escape the moon's weak gravity and replenish Jupiter's vast magnetosphere with fresh material. These plumes create a donut-shaped ring of ionized gas around Jupiter, a dynamic feature that astronomers call the Io plasma torus. It's as if the moon is bleeding its innards into space, feeding its parent planet with a steady diet of volcanic exhaust. Yet for all its chaos, Io offers a masterclass in celestial mechanics. Its hyperactivity challenges traditional notions of how moons cool and solidify over time. Most moons, like Earth's, lose their internal heat billions of years ago, becoming geologically stagnant. Io defies that timeline, proving tidal forces alone can keep a world molten indefinitely. This has implications far beyond our solar system. Exomoons orbiting gas giants in other star systems might harbor similar volcanic extremes, hidden oases of heat in the frigid depths of space. And then there's the irony. Io's eruptions might indirectly make life possible elsewhere. The same tidal heating that ravages Io also warms Europa's subsurface ocean, keeping it liquid beneath miles of ice. In a cosmic twist, Io's suffering could be Europa's salvation, providing the energy needed to sustain a habitable environment next door. So while Io may be a hellish wasteland, it's also a revelation, a reminder that even in the quiet corners of a star system, forces beyond our imagination are at work, bending worlds to their will and rewriting the rules of planetary science with every explosive eruption. If you think acid rain is bad on Earth, Venus scoffs at our feeble chemistry. Its clouds aren't just laced with sulfuric acid, they're essentially a roiling mist of battery acid, concentrated enough to dissolve lead, steel, and even spacecraft armor in a matter of hours. This isn't a gentle drizzle, it's a perpetual, planet-wide acid bath where droplets of sulfuric acid hover in the thick atmosphere, occasionally combining into corrosive downpours that evaporate before they even reach the scorching surface below. What makes Venus's acidic embrace so extreme? Blame a runaway greenhouse effect gone horribly right. The planet's thick carbon dioxide atmosphere traps heat with ruthless efficiency, baking the surface to 860 degrees Fahrenheit, hot enough to melt lead. Up in the clouds, where temperatures are relatively cooler at around 170 degrees, sulfur dioxide from ancient volcanic eruptions mingles with trace water vapor. Sunlight triggers a chemical nightmare, transforming these gases into sulfuric acid through reactions so efficient they'd make an industrial chemist weep. The result, a cloud deck stretching 30 to 40 miles high, composed almost entirely of acid aerosols, refracting sunlight into that eerie yellowish glow that makes Venus look deceptively serene from afar. But here's where it gets worse for anything daring to visit. The acid isn't just present, it's aggressive. When Soviet probes like Venera 13 parachuted into this hellscape in the 1980s, their titanium hulls were eaten alive within minutes. Cameras barely had time to snap photos of the rocky surface before succumbing to the corrosive soup. Modern simulations suggest that even advanced alloys would last mere days before crumbling into metallic slurry. The clouds don't just obscure Venus, they guard it like a chemical moat, vaporizing intruders with the indifference of a dragon lounging in a lake of fire. Yet for all its hostility, Venus's acidic shroud holds clues to one of cosmology's biggest mysteries: how habitable worlds turn deadly. Scientists suspect Venus wasn't always this way. Billions of years ago, it might have had shallow oceans and a temperate climate until a cascade of volcanic eruptions pumped the atmosphere full of greenhouse gases, boiling away the water and triggering the acid formation cycle we see today. The sulfuric acid clouds act like a planetary-scale chemical fingerprint, preserving evidence of that ancient catastrophe. By studying them, we're not just decoding Venus, we're reading a cautionary tale about how easily a planet's climate can spiral into oblivion. And then there's the tantalizing twist: life might still lurk in those toxic clouds. Some astrobiologists propose that certain acid-loving microbes on Earth, like those in Yellowstone's hot springs, could theoretically survive in Venus's upper cloud layers where temperatures and pressures are almost bearable. It's a long shot, but if anything's going to thrive in a sulfuric acid sky, it would rewrite the rules of biology as we know them. So while Venus's atmosphere might seem like nature's most elaborate keep-out sign, It's also a laboratory of extremes, teaching us about planetary evolution, climate catastrophes, and the outer limits of where life might cling. Next time you see Venus shining softly in twilight, remember, behind that golden haze lies a world where the very air is poison and the clouds are made of pure, undiluted fury. Deep inside a super-Earth, a type of planet up to 10 times more massive than our own pressures, reach levels so extreme they rewrite the rules of chemistry. We're talking about crushing forces exceeding 100 million times Earth's atmospheric pressure, enough to crumple diamond like tissue paper. At these unimaginable depths, hydrogen, the universe's simplest element, undergoes a transformation so profound it becomes metallic, a phase of matter that doesn't exist naturally anywhere on Earth. Picture a fluid with the shimmering conductivity of copper, yet made entirely of compressed hydrogen atoms squeezed so tightly their electrons break free, forming a quantum soup that flows without resistance. This bizarre state of matter wasn't just dreamed up in theory. In 2017, scientists at Harvard finally recreated metallic hydrogen in labs using diamond anvils, devices that crush samples between two gem-quality diamonds with pressures rivaling those at Jupiter's core. The experiment confirmed what physicists had suspected for decades. Under enough force, even the most familiar substances can morph into something entirely alien. Now imagine entire oceans of this metallic hydrogen sloshing beneath the clouds of super-Earths, their electrons behaving more like a collective fluid than individual particles. The implications are staggering. These electron seas could generate planet-sized magnetic fields, potentially stronger than Jupiter's legendary magnetosphere. But metallic hydrogen isn't the only oddity birthed by such pressures. Deeper still, carbon might crystallize into structures far stranger than diamond, perhaps a form where each atom bonds to 8 neighbors instead of 4, creating a super-dense lattice that could sink through normal diamond like a stone through water. Even oxygen, typically a gas, would become a solid metal at these extremes, possibly forming intricate layers with other elements like a cosmic millefeuille. The very concept of solid and liquid blurs as materials enter a hybrid state where they're simultaneously crystalline and fluid, a phenomenon called supersonic ice that's been glimpsed in experiments mimicking exoplanet interiors. What's truly mind-bending is how these extreme conditions might influence a planet's fate. Metallic hydrogen could act as a planetary dynamo, generating magnetic fields that shield against deadly cosmic radiation. Supersonic ice might lubricate tectonic activity on scales that make Earth's continental drift look sluggish, and those ultra-dense carbon phases, they could lock away vast quantities of carbon deep underground, preventing runaway greenhouse effects, or trap them so effectively that the planet becomes a frozen wasteland. Yet for all our theories, super-Earth interiors remain cosmic enigmas. Every new exoplanet discovery sends researchers scrambling to update their models. Some of these worlds might harbor materials we haven't even named, yet substances forged under pressures so intense they defy our current understanding of quantum mechanics. One thing's certain, in the crushing embrace of a super-Earth's core, matter doesn't just bend the rules, it sets them on fire and rewrites them from scratch. Drifting through the void between galaxies, a solitary star named Cs, OGS J175553.2-281633, holds the record for the most isolated object of its kind. Unlike the trillions of stars clustered in galaxies, this lonely traveler floats freely in intergalactic space, untethered from any galactic structure, so distant from its nearest neighbors that its night sky would appear almost entirely black, save for the faint smudges of far-off galaxies. If you stood on a hypothetical planet orbiting this star, you wouldn't see the familiar arc of the Milky Way, just endless, empty darkness stretching into infinity. So how did this star become the universe's ultimate castaway? The answer lies in the violent ballet of colliding galaxies. When massive galaxies like the Milky Way and Andromeda pass too close to one another, their gravitational forces can fling stars outward like stones from a slingshot. Most of these exiled stars end up in the galactic halo, a sparse outer region. But in rare cases, a star gets ejected with such force that it escapes its home galaxy entirely, shot into the emptiness between galaxies at speeds exceeding 1,000 kilometers per second. CEOGS J175553.2-281633 is one of these hypervelocity stars, a cosmic bullet fired during an ancient galactic collision or close encounter with a supermassive black hole. But here's what makes this star truly remarkable. Its isolation isn't just a quirk, it's a clue. By studying its trajectory and composition, astronomers can reconstruct the chaotic events that launched it. The star's metallicity, the abundance of elements heavier than hydrogen and helium, suggests it originated in a galaxy's crowded inner regions where such elements are more common. Its current path points back to the Milky Way center, hinting that our galaxy's supermassive black hole may have catapulted it outward billions of years ago during a period of intense activity. This stellar exile also challenges assumptions about where life could exist. Most searches for habitable planets focus on stars within galaxies where resources are plentiful. But if rogue planets orbit stars like CEOGS J175553.2-281633, they'd be insulated from supernova and gamma-ray bursts, hazards that plague galactic neighborhoods. The downside, these worlds would have no neighboring stars to warm them, relying entirely on internal heat or radioactive decay for energy, a meager lifeline in the freezing depths of intergalactic space. Yet the star's greatest gift might be its perspective. Floating far from the light pollution of galaxies, it offers astronomers an unobstructed view into the intergalactic medium, the thin gas and dark matter that filaments the cosmos. By analyzing how the star's light filters through this pristine environment, scientists can measure the universe's hidden scaffolding, the invisible threads that bind galaxies together. CEOGS J175553.2-281633 is more than a curiosity. It's a cosmic accident with profound implications. Its journey reminds us that galaxies aren't static islands, they're dynamic, messy structures that bleed stars into the void. And somewhere out there, other exiles are drifting through the darkness, each carrying a story of ancient violence written in their light. Somewhere in the vast emptiness between galaxies, invisible bullets are flying, cosmic rays packing so much energy they make the Large Hadron Collider look like a toy. These aren't your average interstellar particles. We're talking about ultra-high-energy cosmic rays, subatomic projectiles moving so fast. Each one carries the kinetic energy of a major league fastball squeezed into a single proton. To put that in perspective, a single one of these particles hits with a force equivalent to dropping a brick on your foot from waist height, except the brick is smaller than an atom. So where do these microscopic powerhouses come from? That's the mystery that's kept astrophysicists awake for decades. The most energetic cosmic ray ever detected, dubbed the "Oh my God" particle, slammed into Earth's atmosphere in 1991 with an energy of 300 exa-electronvolts, millions of times more powerful than anything our most advanced particle accelerators can produce. To achieve that kind of energy, a proton would need to travel at 99.9999999999996% the speed of light. That's so close to light speed, if it raced a photon from the moon to Earth, it would lose by less than the width of a human hair. But here's what really bends the mind. According to our current understanding of physics, these particles shouldn't exist. Over cosmic distances, high-energy protons should lose energy as they collide with the microwave radiation left over from the Big Bang, a phenomenon called the Greisen-Zatsepin-Kuzmin-Gizike cutoff. Yet these ultra-high-energy rays keep arriving, suggesting they either come from nearby sources which we can't identify, or that we're missing something fundamental about how particles interact with the fabric of space-time. The suspects behind these cosmic gunshots range from the dramatic to the bizarre. Some theories point to supermassive black holes at the centers of active galaxies, where magnetic fields billions of times stronger than Earth's could act as natural particle accelerators. Others suggest the decay of exotic, super-heavy dark matter particles left over from the early universe. There's even a fringe hypothesis involving defects in space-time itself, cosmic cracks where energy bleeds into particles like water bursting through a dam. Yet for all their destructive potential, these particles are also cosmic messengers. When they strike Earth's atmosphere, they create cascades of secondary particles, sprawling air showers that detectors like the Pierre Auger Observatory in Argentina can trace back to their approximate origin. The trouble is, their paths get bent by galactic magnetic fields along the way, making their sources frustratingly fuzzy. It's like trying to find a sniper by studying the bullet's impact while someone keeps shaking the crime scene. What's clear is this: ultra-high-energy cosmic rays represent the outer limits of nature's particle physics lab. They challenge our models, hint at undiscovered astrophysical engines, and remind us that the universe still holds forces we can't yet replicate or fully comprehend. Every one that strikes Earth is a flare from the cosmic dark, a whisper of processes so violent they redefine what we thought was possible. And until we crack their code, they remain one of the universe's most electrifying mysteries. When galaxies collide, it's not just stars and gas that crash together. It's the supermassive black holes lurking in their cores, locked in a gravitational death spiral. These titanic mergers unleash energies so vast they momentarily outshine every star in the combined galaxies. Picture two black holes, each weighing billions of times the mass of our Sun, whirling around each other hundreds of times per second before finally merging in a cataclysm that rattles the fabric of space-time itself. The final impact releases more power in an instant than all the stars in the observable universe combined, a flash of energy so brilliant it can be seen clear across the cosmos. These collisions don't just produce blinding light, they send ripples through the very structure of reality. Gravitational waves, first predicted by Einstein a century ago, are born from these violent dances. As the black holes orbit closer, they warp space-time like a pair of spinning bowling balls on a trampoline, sending out waves that travel at light speed across billions of light years. In 2015, humanity detected these waves for the first time using LIGO, confirming black hole mergers as one of the universe's most extreme events. But supermassive black hole mergers dwarf those collisions by orders of magnitude, producing waves with wavelengths so long they could stretch from Earth to the nearest star. Yet the spectacle doesn't end there. As the black holes spiral inward, their immense gravity rips apart the surrounding gas and stars, creating a swirling maelstrom of superheated plasma. Temperatures soar to trillions of degrees, igniting bursts of X-rays and gamma rays powerful enough to sterilize entire galactic neighborhoods. Some mergers even launch jets of charged particles at nearly light speed, beaming deadly radiation across intergalactic space like cosmic blowtorches. For a brief moment, the merger's energy output rivals that of a quasar, an object so luminous it can outshine 1,000 Milky Ways. But here's the twist: these apocalyptic collisions aren't just destructive, they're also creative. The gravitational recoil from a merger can fling the newborn black hole clear out of its host galaxy at speeds exceeding 5,000 kilometers per second, turning it into a rogue wanderer. Meanwhile, the shock waves from the crash compress nearby gas clouds, triggering bursts of star formation that repopulate the galaxy with new stellar generations. It's as if the universe uses these violent encounters to hit the reset button, recycling devastation into rebirth. And then there's the lingering mystery: what happens in the final milliseconds before the black holes merge. Supercomputer simulations suggest their event horizons stretch and twist like taffy before finally snapping together in a process called the ring down, where the merged black hole vibrates like a struck bell before settling into its new, more massive form. Some theories even speculate that these mergers might briefly open wormholes or reveal hidden dimensions, though no evidence exists yet. One thing's certain: when galaxies collide, their black holes don't just merge, they rewrite the rules of physics in their wake, leaving behind echoes of their violence that ripple across eternity. While Earth's seasons shift predictably every few months, Uranus operates on an entirely different timetable, one where winter lasts longer than most human lifetimes. Tilted at a jaw-dropping 98 degrees, this ice giant doesn't just lean slightly like Earth's 23-degree slant. It practically rolls around the sun on its side like a cosmic bowling ball. This radical posture means each pole spends 42 Earth years bathed in relentless sunlight, followed by 42 years of complete darkness. Imagine a summer where the sun never sets, not for days or weeks, but for decades. Then, when the season finally turns, the temperature plummets to -370 degrees Fahrenheit as the pole plunges into a winter so long and dark, it makes Arctic nights look like brief power outages. The effects of this extreme tilt ripple across the entire planet. Sunlight strikes Uranus's poles with far more intensity than its equator, creating temperature inversions that defy typical planetary logic. During solstice, when one pole faces the sun head-on, that hemisphere absorbs so much energy it actually becomes warmer than the equator, a phenomenon unheard of on other worlds. Yet despite this solar bombardment, Uranus's upper atmosphere remains shockingly cold, a paradox that still puzzles scientists. Some speculate the planet's sluggish internal heat flow and complex atmospheric layers act like a cosmic insulator, trapping warmth in ways we don't yet understand. Then there's the weather. With such prolonged exposure to sunlight or darkness, Uranus's atmosphere convulses into storms that dwarf Earth's fiercest hurricanes. When Voyager 2 flew past in 1986, it caught the planet in the throes of its blandest season equinox, yet still recorded winds tearing through the upper atmosphere at 560 miles per hour. During solstice, these tempests likely escalate into planet-sized maelstroms, though no spacecraft has been there to witness the spectacle. The sheer scale of these weather patterns is mind-bending. A single storm could swallow Earth whole and still have room to spare. But the weirdest consequence of Uranus's tilt might be its magnetic field. Unlike Earth's relatively orderly north-south alignment, Uranus's magnetic poles are offset by 60 degrees from its rotational axis, and they wander unpredictably. This creates a magnetosphere that tumbles chaotically as the planet rotates, like a dying top's final wobbles. Solar particles caught in this erratic field may trigger auroras that spiral around the planet in dizzying corkscrews, a light show with no equivalent in our solar system. What caused this planetary identity crisis in the first place? The leading theory suggests a cataclysmic collision billions of years ago, when a protoplanet twice Earth's size slammed into Uranus, knocking it sideways like a billiard ball. The impact might have also ejected most of the planet's primordial heat, explaining why its interior is so frigid compared to Neptune. Every extreme trait, the brutal seasons, the lopsided magnetism, the paradoxical cold, stems from that ancient cosmic car crash. Uranus stands as a stark reminder that the universe has no obligation to make sense by our standards. While other planets rotate with dignified precision, it cartwheels through space, laughing in the face of celestial convention. And somewhere out there right now, one of its poles is either baking under a sun that won't set for generations or shivering in a darkness so profound, it redefines the meaning of night. At the heart of certain distant galaxies, cosmic monsters lurk: quasars, the brightest objects in the universe. A single quasar can outshine 1,000 Milky Ways combined, blazing with the luminosity of 100 trillion suns. This isn't just impressive, it's incomprehensible, a scale of energy so vast it redefines what we thought was possible for celestial objects. The secret to these raging behemoths lies in their engines, supermassive black holes, some weighing billions of times the mass of our Sun. But unlike dormant black holes that sit quietly in space, quasars are powered by black holes in the middle of an all-you-can-eat cosmic buffet. As gas, dust, and even entire stars spiral toward the event horizon, they don't just vanish. They form a swirling, superheated disk called an accretion disk. Friction within this disk heats the material to millions of degrees, turning it into a glowing maelstrom of plasma that radiates energy across the entire electromagnetic spectrum, from radio waves to gamma rays. But here's where it gets even more extreme. The magnetic fields around these black holes twist and channel some of that infalling material into jets shooting outward at nearly light speed. These jets, stretching hundreds of thousands of light years into space, act like cosmic blowtorches, adding to the quasar's already staggering brightness. The energy release is so efficient, it makes nuclear fusion, the process powering stars, look like a flickering candle next to a supernova. What's truly mind-blowing is that quasars aren't just powerful, they're ancient. The light from most quasars we observe has traveled for billions of years, meaning we're seeing them as they were when the universe was young. Back then, galaxies were gas-rich, providing endless fuel for these ravenous black holes. Today, quasars are rarer because their fuel sources have dwindled, leaving many supermassive black holes dormant or dim. Quasars also play a surprising role in shaping their galaxies. The radiation and jets they produce can blow away star-forming gas, effectively putting a cap on how many new stars a galaxy can create. In a way, they're both creators and destroyers, igniting brilliance on a cosmic scale while simultaneously shutting down stellar nurseries. Yet for all their ferocity, quasars have a delicate side. By studying their light, astronomers have mapped the structure of the early universe, using them as backlight to reveal the faintest filaments of gas between galaxies. They're not just cosmic lighthouses, they're time capsules, preserving clues about the universe's most turbulent eras. So next time you gaze at the night sky, remember this: somewhere out there, a quasar is burning brighter than entire galaxies, a testament to the raw, untamed power lurking at the heart of creation. Stretching across the entire sky like a ghostly blanket, the cosmic microwave background is the oldest light in existence, a faint whisper from the universe's infancy. This afterglow dates back to just 380,000 years after the Big Bang, a time when the cosmos cooled enough for atoms to form, allowing light to travel freely for the first time. What we're seeing is essentially the universe's baby photo, a snapshot frozen in time when everything was a seething plasma of particles and radiation, before stars or galaxies even existed. But this isn't just any ancient glow, it's a treasure map of cosmic history. The microwave background isn't perfectly smooth. It's speckled with tiny temperature fluctuations, variations as minute as 1 part in 100,000. These faint ripples, captured in stunning detail by space telescopes like Planck and WMAP, reveal the seeds of all future structure in the universe. Denser regions would eventually collapse under gravity, forming the vast web of galaxies and galaxy clusters we see today. The lighter patches, those became the voids, the great cosmic deserts stretching between galaxies. It's like finding the fossilized imprints of rain droplets that later grew into oceans. What's even more astonishing is how this relic radiation was discovered. In 1965, 2 radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, kept picking up a persistent static noise in their antenna no matter where they pointed it. After eliminating every possible source, from pigeon droppings to electrical interference, they realized they'd stumbled upon the echo of creation itself. That faint hiss, uniform in all directions, matched theoretical predictions of the Big Bang's afterglow. cooling over billions of years to just 2.7 degrees above absolute zero. Yet the cosmic microwave background holds deeper mysteries. Its polarization pattern, subtle swirls imprinted on the light, hint at gravitational waves from the universe's first trillionth of a second, a period called inflation when space itself expanded faster than light. Some researchers believe these patterns could reveal parallel universes or hidden dimensions, though the evidence remains tantalizingly elusive. Even the slight asymmetry in temperature between opposite sides of the sky challenges our assumptions, suggesting the early universe may have been fundamentally lopsided. This ancient light doesn't just illuminate the past, it shapes our future. By studying its fluctuations, cosmologists have calculated the universe's precise composition: 5% ordinary matter, 27% dark matter, and 68% dark energy. It's the ultimate cosmic inventory, etched into the sky for anyone with the right tools to read. And as our telescopes grow more sensitive, this faded glow continues to whisper secrets about the universe's birth, its structure, and perhaps even its ultimate fate. So the next time you tune an old analog radio between stations and hear static, remember, some of that noise isn't just interference, it's the dying breath of the Big Bang, still reverberating 13.8 billion years later. And in its faint crackle lies the story of everything. HD 80606b doesn't orbit its star, it survives it. This gas giant doesn't follow the gentle, circular path of planets like Earth or Jupiter. Instead, it carves a wild, elongated ellipse through space, swinging closer to its star than Mercury does to our Sun before catapulting back out into the frigid depths of its system. At its most distant, the planet shivers at -100 degrees Fahrenheit, but as it hurtles toward its closest approach, temperatures skyrocket to 2,000 degrees in just 6 hours, a shockwave of heat so sudden it triggers supersonic storms capable of vaporizing iron. The secret to this planetary roller coaster lies in its freakishly oblong orbit, the most extreme ever measured for an exoplanet. Most planets, shaped by billions of years of gravitational smoothing, settle into near-circular paths. But HD 80606b, tugged by a neighboring star in its binary system, never had that chance. Its path resembles a comet's more than a planet's, with an eccentricity of 0.93, where 0 is a perfect circle and 1 is a runaway trajectory. Every 111 days, it endures a cosmic whiplash, streaking so close to its star that tidal forces stretch its atmosphere like taffy before slingshotting it back into the cold. What happens during these close encounters isn't just dramatic, it's transformative. Infrared observations reveal the planet's atmosphere doesn't just heat up, it erupts. Layers of gas, frozen solid during its long winter, thaw and expand at breakneck speeds, spawning winds that scream across the surface at 11,000 miles per hour. These aren't ordinary weather patterns, they're global firestorms, redistributing heat so violently that the planet's day side and night side swap temperatures within days. The thermal shockwaves ripple through the atmosphere, triggering shock fronts that glow brighter than the star itself in certain wavelengths. Yet HD 80606b's torment holds clues to one of astronomy's biggest puzzles: how gas giants evolve. Most hot Jupiters, gas giants baking near their stars, have circularized orbits, their wild youth smoothed by time. This planet, frozen mid-chaos, offers a rare snapshot of that process in action. With each brutal pass, tidal forces sap a bit of its orbital energy, gradually rounding its path. In a few 100 million years, its death-defying swings may calm into a tamer loop, but for now, it's a living lab of orbital mechanics pushed to the brink. And there's a poetic twist to its fury. The same gravitational dance that tortures this world might also spare it. Some models suggest its extreme orbit prevents the total atmospheric erosion that plagues other hot Jupiters. The brief, searing visits to its star leave just enough time for the planet's gravity to cling to its gases before retreating to cooler safety. It's a delicate balance. One wrong nudge, and the atmosphere could boil away entirely or freeze into permanent twilight. So while HD 80606b might seem like a cosmic oddity, it's also a reminder. The universe loves extremes, but it also abhors waste. Even in the most violent orbits, there's a rhythm, a reason, a lesson written in fire and ice across the skies of a world that refuses to play by the rules. He 1327-2326 isn't just a star, it's a cosmic time capsule, a relic from an era when the universe was still figuring out how to forge elements. This ancient beacon, lurking 13,000 light-years away, holds a staggering distinction. It's the most metal-poor star ever discovered, with an iron abundance 1,000,000 times lower than our Sun's. But here's the twist: when astronomers say metal, they're not talking about asteroids or rings. In stellar terms, any element heavier than hydrogen and helium qualifies as metal, the building blocks of planets and life itself. He 1327-2326 is so pristine. Its composition mirrors the primordial gas that filled the cosmos just a few 100 million years after the Big Bang. What makes this star so extraordinary isn't just what it lacks, it's what its poverty reveals. Born from a cloud nearly untouched by previous generations of stars, its atmosphere acts like a forensic snapshot of the early universe. While most stars, including our Sun, are enriched by the ashes of supernova, He 1327-2326 chemistry suggests it formed from material polluted by just one or two ancestral stars, likely massive, short-lived giants that exploded in hypernova, blasting the first heavy elements into the void. Its atmosphere contains trace amounts of carbon and nitrogen but almost no iron, a fingerprint of those first fumbling attempts at cosmic alchemy. This star shouldn't exist, at least not according to classic stellar models. Conventional wisdom says stars this metal-poor would have needed far more mass to ignite nuclear fusion, yet He 1327-2326 is a modest subgiant, barely holding onto hydrogen burning in its core. Its survival forces astronomers to reconsider how the first stars formed. Perhaps turbulence in primordial gas clouds allowed smaller stars to collapse, or maybe exotic cooling mechanisms helped them condense without the heavy elements that typically radiate heat away. Either way, this star is a living paradox, a fragile beacon from a time when the rules of star birth were still being written. Yet its greatest gift might be the questions it raises. If stars like He 1327-2326 could form with almost no metals, could there be even purer ones lurking in the galactic halo, stars made of nothing but hydrogen and helium? And what does its unusual carbon enrichment say about the very first supernova? Some theorists suggest these early explosions were fundamentally different, asymmetric, maybe, or riddled with unstable isotopes that decayed swiftly. Every photon from this star carries clues, a cipher waiting to be cracked. He 1327-2326 is more than a celestial curiosity. It's a bridge to the universe's darkest age. Its light, unchanged for over 13 billion years, lets us stare directly into the cosmic dawn, a time when the first stars were barely flickering to life. And as we study its frail glow, we're not just observing history, we're rewriting it, one atomic whisper at a time. The Tarantula Nebula isn't just birthing stars, it's conducting a full-blown cosmic fireworks show. Packed into a corner of the Large Magellanic Cloud, this sprawling stellar nursery churns out new stars at a rate so furious, it puts every other known region in the local universe to shame. If the Milky Way's star-forming hubs are quiet suburbs, the Tarantula is a downtown metropolis at rush hour, complete with traffic jams of gas, shockwaves from supernova, and skyscrapers of radiation carving through the chaos. At the heart of this maelstrom lies R136, a cluster of young, hyperactive stars so massive and luminous they defy conventional stellar physics. The brightest among them, R136A1, tips the scales at over 250 solar masses, a behemoth so unstable it's constantly shedding weight like a prize fighter sweating off pounds before a match. This star alone pumps out 9 million times the luminosity of our Sun, bathing the surrounding nebula in ultraviolet radiation so intense it ionizes hydrogen gas across thousands of light years. The effect is both creative and destructive. While the radiation triggers new star formation by compressing nearby gas clouds, it also blows them apart, sculpting towering pillars and cavities that resemble a celestial spiderweb, hence the nebula's name. But radiation isn't the only force reshaping this region. The tarantula's stellar winds are galactic hurricanes with particles streaming outward at speeds exceeding 2,000 miles per second. When these winds collide with slower-moving gas, they create shock fronts that glow in X-rays, visible to telescopes like Chandra as ethereal loops and bubbles. Some of these structures span hundreds of light years, serving as cosmic pressure cookers where new stars are squeezed into existence. It's a self-perpetuating cycle. Each generation of stars births the next, their short, violent lives ending in supernova that seed the nebula with heavy elements and trigger yet another round of starbirth. The tarantula's most stunning feature might be its sheer scale of productivity. While the Orion Nebula, Earth's closest star factory, forms about 1 star per year, the tarantula generates roughly 1 solar mass worth of stars every few thousand years. Over the past 25 million years, it's birthed enough stars to populate a small galaxy. This frenzy leaves behind a glittering graveyard of stellar remnants, neutron stars, black holes, and vast shells of debris from past explosions, all woven into the nebula's tapestry. Yet this chaos isn't random, it's a laboratory for understanding how the universe's first star clusters might have behaved. The tarantula's metallicity, lower than the Milky Way's but higher than pristine primordial gas, mirrors conditions in the early cosmos when the first supermassive stars lit up the darkness. By studying its chemistry and dynamics, astronomers get a front-row seat to processes that shaped the universe's infancy. What's truly humbling is the ephemeral nature of it all. The tarantula won't rage forever. In another few million years, its most massive stars will have burned out, their deaths leaving behind a quieter, more diffuse region. But for now, it stands as a testament to the universe's capacity for both creation and destruction, a place where stars aren't just born but forged in the crucible of extremes. And somewhere in that tangled web of gas and light, the next cosmic titan is taking shape, ready to ignite and carve its own mark into the nebula's ever-changing story. Approaching a black hole's event horizon isn't just dangerous, it's a one-way trip into a cosmic time warp. Imagine an astronaut brave or reckless enough to venture close, sending pulses of light back to a distant observer watching from a safe orbit. At first, the signals arrive at a steady pace, but as the astronaut nears the point of no return, something eerie happens. The light pulses begin stretching, arriving farther apart, their frequency shifting red as gravity battles against the photons trying to escape. To the observer, the astronaut's movements slow to a crawl, their image freezing like a buffering video as time itself grinds to a near halt. But here's the paradox for the astronaut: time feels normal. Their watch ticks steadily, their heartbeat remains unchanged. They'd cross the horizon without even realizing it, while to the outside universe, they'd appear suspended there, forever fading into darkness. This is time dilation cranked to its most extreme, a consequence of Einstein's general relativity, where gravity doesn't just bend space, it warps time. Near a black hole, the gravitational pull is so intense that time stretches like taffy. At the event horizon, the point where escape becomes impossible, time effectively stops relative to the rest of the universe. It's as if the black hole presses pause on reality for anyone watching from afar. The closer you get, the more you step out of sync with cosmic time. A minute for the astronaut could be years, centuries, or even millennia for those far away, depending on the black hole's size. To grasp how extreme this gets, consider a hypothetical scenario. If you could hover just above the horizon of a supermassive black hole like Sagittarius, a star at our galaxy's center-holding position with some impossibly strong thruster, you'd experience time so slowed that a single hour for you could equate to decades passing on Earth. Miss a dinner reservation back home, and by the time you returned, civilizations might have risen and fallen. This isn't science fiction. It's the universe's own version of a time machine where gravity's grip rewrites the rules of cause and effect. Light itself isn't immune to this distortion. Photons emitted near the horizon lose energy fighting gravity, a phenomenon called gravitational redshift. Their wavelengths stretch so dramatically that visible light could shift into radio waves, then fade beyond detection. The astronaut's final signal to the outside world wouldn't just slow down, it would dissolve into nothingness, a ghostly whisper swallowed by the void. Yet the most mind-bending implication isn't the stretching of time, it's the way black holes force us to confront the illusion of a universal now. In daily life, we assume time flows equally for everyone. But relativity shatters that notion. There's no cosmic clock ticking in unison across the universe. Time is local, personal, shaped by gravity and motion. A black hole doesn't just trap matter. It locks moments in amber, preserving them in an infinite, almost for outside observers, while carrying those who cross the horizon into a reality where time and space trade places. This extreme time warp isn't just a theoretical curiosity. It leaves fingerprints astronomers can detect. Matter spiraling into black holes doesn't vanish instantly. It lingers in a fiery accretion disk, its light stretched and dimmed by these relativistic effects. By studying those distortions, we map the warped spacetime around black holes, testing Einstein's predictions in nature's most violent laboratories. So while we may never send humans close enough to experience this time dilation firsthand, black holes offer a profound lesson. Time isn't rigid. It's fluid, malleable, and under the right conditions, or rather, the most extreme ones, it can bend until it nearly breaks, revealing a universe far stranger than our everyday experience suggests. And somewhere out there, right now, a black hole is twisting time into knots, proving once again that the cosmos operates by rules that defy intuition. Eta Carinae isn't just a star, it's a cosmic powder keg on the verge of detonating. This hypergiant, located 7,500 light-years away in the Carina Nebula, is one of the most massive and unstable stars ever observed, weighing in at over 100 times the mass of our Sun and shining with the brilliance of 5 million suns combined. But what makes Eta Carinae truly extraordinary isn't just its size. It's the star's violent mood swings, its history of catastrophic eruptions, and the looming threat of a supernova that could outshine the full moon in Earth's night sky. In the mid-19th century, astronomers witnessed Eta Carinae undergo an eruption so colossal it became the second brightest star in the night sky for years, despite its staggering distance. The event, known as the Great Eruption, hurled enough material into space to form 10 suns, creating the Homunculus Nebula, a bipolar cloud of gas and dust that now cradles the star like a glowing hourglass. Today, telescopes reveal intricate filaments and shockwaves within this nebula, remnants of a stellar tantrum so powerful it defied all conventional models of stellar behavior. Most stars don't survive such outbursts intact, yet Eta Carinae somehow clung to existence, though permanently scarred and fundamentally altered by the trauma. But the Great Eruption might have just been a warm-up act. Eta Carinae is now a ticking time bomb, its core teetering on the edge of collapse. The star's instability stems from its extreme mass, which generates such intense radiation pressure that its outer layers are constantly fighting to escape gravity's grasp. Every few decades, smaller eruptions eject additional material, like a pressure valve sporadically releasing steam. These outbursts hint at the titanic forces churning inside the star, where turbulent nuclear reactions battle to maintain equilibrium. What's truly terrifying is the scale of destruction Eta Carinae's eventual supernova could unleash. When it finally explodes, and astronomers agree it's not a question of if, but when the blast will be visible in broad daylight on Earth, possibly outshining Venus for weeks. The explosion might even produce a gamma-ray burst, a focused beam of high-energy radiation that could, if pointed at Earth, strip away our ozone layer and trigger a mass extinction. Even without that worst-case scenario, the supernova's shockwaves will plow through the surrounding nebula at millions of miles per hour, sculpting new star-forming regions in its wake. Yet for all its destructive potential, Eta Carinae is also a goldmine for science. Its erratic behavior challenges our understanding of stellar evolution, forcing astronomers to reconsider how massive stars live and die. The Homunculus Nebula acts as a time capsule, preserving details of past eruptions that help decode the star's internal mechanics. And the star's inevitable demise will provide front-row seats to a supernova spectacle unlike anything humanity has witnessed in recorded history, a chance to study the death throes of a true stellar titan. Eta Carinae is more than an impending cosmic cataclysm. It's a testament to the universe's capacity for both chaos and creation. Its explosions seed the cosmos with heavy elements, its light illuminates the structure of distant dust clouds, and its very existence pushes the boundaries of astrophysics. So while we watch and wait for its final act, the star continues to teach us, reminding us that even the most violent forces in the universe are also the most illuminating. Jupiter's auroras don't just dance, they rage. While Earth's northern and southern lights paint the sky with delicate greens and purples, Jupiter's polar displays explode with energy so intense they could power human civilization for centuries. These aren't just pretty lights, they're colossal storms of charged particles, swirling in patterns larger than entire planets and glowing across the electromagnetic spectrum, from radio waves to X-rays. Imagine an aurora so bright it outshines the sun's ultraviolet output, or so vast it could engulf Earth whole without breaking stride. That's the scale of Jupiter's polar fireworks, a spectacle unmatched anywhere else in our solar system. What fuels this otherworldly light show? The answer lies in a cosmic partnership between Jupiter and its volcanic moon, Io. While Earth's auroras are sparked by solar wind particles funneled toward our poles, Jupiter's arise from its own backyard. Io, the most geologically active body in the solar system, spews sulfur dioxide into space at a rate of 1 ton per second. Jupiter's immense magnetic field captures these particles, accelerating them to near-light speeds along magnetic field lines toward the poles. When these high-energy ions slam into atmospheric hydrogen, the collisions unleash ultraviolet and X-ray flares visible to telescopes like Hubble and Chandra. The result is an auroral ring of fire, a perpetual storm of radiation that could fry electronics and strip flesh from bone in seconds. Yet Jupiter's auroras aren't just bigger, they're fundamentally different. Earth's lights flicker and fade with solar activity, but Jupiter's blaze relentlessly, powered by the planet's own rotation. Jupiter spins so fast, once every 10 hours, that its magnetic field whips charged particles into a frenzy, generating currents strong enough to light up cities if cities existed in the Jovian atmosphere. The auroras even pulse rhythmically, a heartbeat-like signature caused by Jupiter's magnetic field lines snapping like cosmic rubber bands, flinging particles inward with enough force to create secondary auroral ovals inside the main rings. The most jaw-dropping feature, these auroras aren't confined to the poles. Jupiter's magnetic field is so complex, tangled by interactions with Io and other moons, that auroral spots appear near the equator, dancing in sync with the orbits of volcanic satellites. Sometimes magnetic reconnection events trigger explosions bright enough to briefly outshine the planet's reflected sunlight, like a flashbulb going off in deep space. But here's what makes Jupiter's light show truly alien. It's not just a visual phenomenon. The planet's auroras generate roaring radio emissions detectable from Earth, sounding like ocean waves crashing against a cosmic shore. These radio waves, produced by electrons spiraling along magnetic fields, are so powerful they were mistaken for extraterrestrial signals when first discovered in the 1950s. Even the X-ray component defies expectations, pulsing unpredictably, sometimes flaring in sync with solar wind changes, other times marching to the beat of Eo's orbital rhythm. Studying these auroras isn't just about cosmic spectacle, it's a masterclass in planetary magnetism. Jupiter's magnetic field is 20,000 times stronger than Earth's, a product of its churning metallic hydrogen interior. By mapping auroral patterns, scientists indirectly probe the depths of Jupiter's hidden dynamo, unraveling mysteries about how planetary magnetic fields form and evolve. Each flicker, each pulsation, whispers secrets about the currents surging beneath those striped clouds. So while Earth's auroras might be the most photogenic, Jupiter's are the undisputed champions of raw power. They're a reminder that magnetism isn't just a force, it's an artist painting the skies of worlds across the cosmos with brushes dipped in radiation and plasma. And somewhere above those stormy cloud tops right now, particles from a volcanic moon are igniting a light show that makes our northern lights look like a match struck in a hurricane. Ton 618 isn't just a black hole. It's a cosmic colossus so vast it defies comprehension. Clocking in at 66 billion times the mass of our Sun, this gravitational behemoth dwarfs even the supermassive black holes lurking at the hearts of most galaxies. If placed at the center of our solar system, its event horizon would swallow everything out past Pluto, engulfing planets like specks of dust in a vacuum cleaner. But what truly boggles the mind isn't just its size, it's how such an unfathomable object could even come to exist. The story of Ton 618 begins in the early universe, a time when galaxies were little more than dense clouds of primordial gas. Most supermassive black holes grow gradually, feeding on gas and stars over billions of years. But Ton 618 extreme mass suggests a different origin, perhaps a direct collapse black hole, where an entire gas cloud imploded in on itself, skipping the star stage entirely. Alternatively, it might have gorged on an unprecedented diet during the cosmic dawn, feasting on entire galaxies in a feeding frenzy that left it bloated beyond reason. The environment around it offers clues. Ton 618 powers a quasar so luminous, it outshines the Milky Way by a factor of 140 trillion, a testament to the staggering energies at play as matter spirals into oblivion. Yet even as it devours, Ton 618 shapes its surroundings with ruthless efficiency. The radiation blast from its accretion disk creates pressure waves that push star-forming gas outward, effectively sterilizing its host galaxy. Meanwhile, jets of plasma shot from its poles at near light speed carve cavities in intergalactic space, leaving scars visible across millions of light years. This isn't just a black hole, it's a cosmic architect, sculpting the universe on scales we're only beginning to map. What's truly humbling is how Ton 618 challenges our understanding of physics. Black holes this massive exist in a twilight zone between known phenomena and theoretical speculation. Some models suggest their event horizons might exhibit quantum effects normally seen only in subatomic particles. Others propose their immense gravity could warp spacetime into configurations that defy classical relativity. Each photon we detect from its quasar carries traces of these extreme conditions, offering glimpses into regimes where the laws of physics as we know them begin to fray. Ton 618 stands as a monument to the universe's capacity for extremes, a reminder that even in the quiet vastness of space, there are monsters lurking in the dark, rewriting the rules of existence with every passing eon. And somewhere out there, even larger black holes may wait, hidden in the voids between galaxies, their sheer mass still unmeasured and their origin still shrouded in mystery. Mars doesn't do gentle breezes, it unleashes planet-sized tantrums of dust so vast they shroud the entire world in a choking, rust-colored haze for months on end. These aren't just regional sandstorms, they're global apocalypses capable of blotting out the sun across every mountain, canyon, and crater from pole to pole. When a mega storm kicks up, it doesn't just obscure the surface, it rewrites the planet's weather patterns, alters atmospheric pressure, and even temporarily changes the color of Mars as seen from Earth. Winds may not howl as fiercely as you'd expect. Mars's thin atmosphere means gusts rarely exceed 60 miles per hour, but what the storms lack in brute force, they make up for in persistence and sheer scale. Fine dust particles lofted high into the atmosphere can linger for weeks, turning the sky from pink to a sinister ochre and plunging temperatures into chaos. The mechanics behind these storms read like a recipe for atmospheric chaos. It starts with temperature imbalances. Mars's elliptical orbit means its southern hemisphere experiences more extreme seasons than the north. When summer hits, sunlight warms the surface unevenly, creating powerful updrafts that rip dust particles from the ground. Once airborne, these particles absorb even more heat, fueling stronger winds that lift more dust in a self-sustaining cycle. Within days, what began as a local gust can grow into a continent-sized tempest. By the time the storm peaks, dust reaches altitudes of 40 miles, forming a suffocating blanket that traps infrared radiation and sends surface temperatures plummeting while upper atmospheric layers heat up dramatically. For robotic explorers like NASA rovers, these storms are existential threats. Solar-powered missions like Opportunity met their end when global storms blocked sunlight for so long, their batteries drained beyond recovery. Even nuclear-powered Curiosity had to weather reduced visibility and instrument malfunctions during the 2018 planet-encircling event. The dust doesn't just obscure cameras, it clogs gears, coats solar panels, and grinds into moving parts like abrasive powder. Future human colonists would face even deadlier challenges. Breathing filters clogged within hours, solar farms rendered useless, and outdoor activities halted for months. The psychological toll of living under perpetual twilight with no view of the stars or sun could prove as crippling as the technical hurdles, yet these storms also hold clues to Mars's ancient past. The dust itself is magnetized, hinting at a time when the planet had a global magnetic field to align its minerals. Storm patterns may reveal hidden water reserves too. As dust settles, it sometimes exposes subsurface ice near the poles. And the way storms transport material globally could explain why Mars's surface appears so uniformly rusty. Dust from iron-rich regions gets endlessly redistributed, painting the planet in a single, monotonous palette over eons. Perhaps most intriguing is how these tempests mirror Earth's own climate systems, just dialed to 11. The feedback loops between dust, temperature, and wind resemble processes in our deserts and oceans, offering a stripped-down model of atmospheric dynamics. Studying them helps predict how climate change might amplify dust storms on our own world, where particulate pollution already affects millions. Mars's dust storms are more than meteorological curiosities, they're reminders of nature's capacity for organized chaos. A planet that seems static at first glance is in fact a whirlwind of activity, its thin atmosphere capable of planet-altering feats. And as we prepare to send humans into that fray, these storms stand as both warning and teacher. The universe doesn't care about our plans, but if we watch closely, it might just show us how to survive them. The Boötes void isn't just empty, it's a cosmic desert so barren it challenges everything we know about how the universe organizes matter. Spanning an astonishing 330 million light-years across, This vast spherical region contains only a handful of galaxies where astronomers would expect to find thousands. To put that in perspective, if the Milky Way were a single grain of sand in this void, the next grain would be over 1,500 miles away. This isn't just a gap, it's a staggering absence, a hole punched through the cosmic web so vast it defies easy explanation. When astronomers first stumbled upon the void in the 1980s, they assumed it had to be an error. The universe, after all, is supposed to be roughly uniform on large scales, with galaxies clustered like foam in a bubble bath. But the Boötes void flips that assumption on its head. Its near-total emptiness suggests either a freak statistical anomaly or a gap in our understanding of how matter clumps together. Some theorists propose it's the result of a cataclysmic collision between smaller voids in the early universe, like soap bubbles merging into one giant cavity. Others speculate it could be evidence of an ancient universe-scale structure, a scar left behind by something we've yet to comprehend. The void's eerie silence isn't just a curiosity, it's a forensic puzzle. The few galaxies that do cling to existence inside it are oddballs, often isolated and strangely quiet, as if starved of the raw materials needed to form new stars. One leading hypothesis suggests that dark energy, the mysterious force accelerating the universe's expansion, may have played a role in emptying the void over billions of years. Imagine blowing up a balloon with weak spots, regions where the rubber stretches too thin and eventually tears. The Boötes void might be such a tear, a place where dark energies push overwhelmed gravity's pull, leaving behind a cosmic dead zone. Yet the void isn't entirely lifeless. In 2015, astronomers discovered a faint, diffuse glow within it, a whisper of hydrogen gas lit up by distant background radiation. This ghostly signal hints that the void might not be as empty as it seems, just sparsely populated with ultra-dark galaxies or rogue stars flung into the abyss. Alternatively, it could be evidence of primordial conditions, a pocket of the universe that never fully participated in the galaxy-forming frenzy of the cosmic dawn. The Boötes void forces us to confront how little we truly understand about the universe's structure. It's a reminder that for every rule we think governs the cosmos, there are exceptions, places where the puzzle pieces don't quite fit. And if voids like this can exist, what other anomalies might be lurking in the darkness, waiting to upend our theories? The Boötes void isn't just a curiosity, it's a challenge, a cosmic dare to look deeper and question harder. Because sometimes the most profound mysteries aren't in what the universe shows us, but in what it hides. WASP 76b isn't just hot. It's a world where the very concept of weather gets rewritten in molten metal and supersonic winds. This ultra-hot Jupiter, orbiting precariously close to its host star, has a party trick that sounds ripped from a sci-fi nightmare. It rains iron, not water, not methane, actual vaporized metal that condenses into droplets on the night side and plummets like 1,000 tiny anvils. And this isn't poetic exaggeration. Astronomers have detected the spectral signature of iron vapor in its atmosphere, along with the telltale absence of that signature on the cooler night side, where the metal presumably cools and falls. The secret to this extreme metallicity lies in the planet's tidal lock, one side permanently scorched by its star, the other frozen in eternal shadow. The day side broils at over 4,400 degrees Fahrenheit, hot enough to vaporize not just iron but even titanium. Molecules here don't stand a chance. They're ripped apart into their constituent atoms, creating an atmosphere more like a plasma soup than the nitrogen-oxygen mix we breathe. But as this superheated gas is whipped toward the night side by winds exceeding 11,000 miles per hour, temperatures plummet by nearly 3,000 degrees. The iron, once suspended as a glowing mist, suddenly condenses into liquid droplets, then solidifies into tiny pellets that streak through the frigid darkness. What's truly bizarre is how this cycle mirrors Earth's water cycle, just swapped with materials that belong in a forge rather than a forecast. On our planet, water evaporates, forms clouds, and rains back down. On WASP 76b, the same process happens with iron, calcium, and even magnesium, creating a meteorology of molten metals. The boundary between day and night isn't just a twilight zone. It's a dystopian smelting front where the atmosphere itself undergoes a phase change, like a cosmic blacksmith's anvil cooling red-hot steel. This isn't just a curiosity, it's a window into how chemistry operates under extreme conditions. The planet's atmosphere lacks the temperature-moderating effects of Earth's oceans or vegetation, allowing heat differentials to run wild. That imbalance drives winds so violent they could circumnavigate our planet in under 4 hours, carrying metal vapor like a celestial conveyor belt. And because WASP 76b orbits its star every 1.8 Earth days, this cycle of vaporization and condensation plays out in hyperspeed, a relentless metallurgical loop that shapes the planet's entire climate. Yet the most haunting detail might be the silence of that iron rain, with no solid surface to speak of, just a hazy, pressurized atmosphere transitioning seamlessly into a supercritical fluid deeper down. The falling metal likely dissolves back into the abyss before it ever hits ground. It's a storm without thunder, a downpour without puddles, unfolding in a world where the very laws of weather obey a logic we're only beginning to decipher. WASP 76b forces us to confront the sheer diversity of planetary environments. If a world can turn something as sturdy as iron into fleeting atmospheric decoration, what other alchemical wonders might be lurking out there? Every drop of that iron rain is a reminder. The universe doesn't just defy expectations, it invents entirely new rules for us to discover. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a signal so powerful and unusual that the astronomer who discovered it scribbled, "Wow." In the margin of the printout, giving it its legendary name, for 72 seconds, a burst of radio waves blared at a frequency of 1420 MHz, a band where natural cosmic noise is virtually silent and where scientists had theorized extraterrestrial civilizations might transmit. The signal wasn't just strong, it was targeted, appearing to originate from a specific point near the constellation Sagittarius, and then vanishing as abruptly as it began. Decades later, despite exhaustive searches, nothing like it has ever been detected again. The WOW signal's uniqueness lies in its precision. It matched almost exactly what astronomers expected an artificial interstellar broadcast might look like: narrowband, intense, and drifting slightly in frequency as Earth rotation altered the telescope's alignment. Natural cosmic phenomena like pulsars or quasars don't behave this way. They're usually broadband or erratic, not a laser-focused blip on a quiet frequency. The signal's intensity also suggested a transmitter far more powerful than anything humanity could muster, something capable of projecting across interstellar space with crystal clarity. Yet the mystery deepens when you consider the alternatives. Could it have been a rogue satellite or secret military transmission? Unlikely. No known human technology at the time operated on that exact frequency without leaving traces elsewhere. A passing comet's hydrogen cloud, a later theory suggested this, but the comets in question weren't anywhere near the signal's origin when it was detected. The more you rule out, the more the alien hypothesis lingers, not as sci-fi fantasy, but as the least implausible explanation science can't yet dismiss. What makes the WOW signal endure in scientific memory isn't just its unresolved origin, it's the tantalizing possibility it represents. That brief blip embodies the essence of the Fermi paradox. If the universe is teeming with life, where is everybody? Maybe they're sending signals we're barely equipped to catch, or maybe we caught the cosmic equivalent of a single, unintentional echo. Either way, the WOW signal remains astronomy's most infamous ghost, a whisper from the void that refuses to be explained, a reminder that the universe might still have surprises lurking in the static. And so the search continues, with modern telescopes scanning the same patch of sky, hoping for a repeat performance that never comes. Until then, the WOW signal stands as a monument to curiosity, a 72-second enigma that proves sometimes the most profound discoveries aren't about what we find, but what we can't forget. From black holes where time itself bends to breaking point, to planets where molten metal rains from the sky, we've journeyed through 30 of the universe's most jaw-dropping extremes, each one pushing the boundaries of what we thought possible. These aren't just cosmic curiosities, they're radical reminders that the universe operates on a scale beyond human intuition, where the laws of physics twist into surreal new forms. Imagine a nebula colder than the void of space, a star so isolated its night sky is Chinese letter empty, or a magnetic field so strong it could rip atoms apart from thousands of miles away. Every fact we've explored peels back another layer of cosmic audacity, revealing a reality far stranger and far more spectacular than fiction. What ties these extremes together isn't just their violence or scale, it's how they force us to rethink the fundamentals. Time isn't absolute, it's warped by gravity. Matter isn't just solid, liquid, or gas, it's neutron degenerate soup, metallic hydrogen, or supersonic ice. Even emptiness isn't truly empty. The Boötes void haunts the cosmos like a ghost, while ultra-high-energy cosmic rays scream through the dark, carrying secrets we've yet to decode. These phenomena don't just defy expectations, they rewrite the rulebook entirely, proving the universe is a laboratory of the unimaginable. And here's the thrilling part, we've only scratched the surface. For every extreme we've catalogued, there are countless others waiting to be discovered, perhaps a quasar brighter than anything we've seen, a rogue black hole drifting unseen between galaxies, or a planet with conditions even more bizarre than iron rain. The cosmos specializes in the improbable, and the next great discovery might be lurking in data we've already gathered, or hiding just beyond the reach of our telescopes. So what's your favorite cosmic extreme? The star that burns at 500 million degrees, or the nebula that defies absolute zero? The magnetic monster that warps reality, or the exoplanet where glass falls sideways at bullet speed? Drop your pick in the comments, and while you're there, take a second to look up at the night sky. Because out there, right now, the universe is cooking up new extremes beyond our wildest dreams. And who knows, the next mind-bending discovery might have your name on it. Until then, keep exploring. The cosmos isn't just extreme, it's unstoppable.